Okay. We are live.
All right. I would say it's 9 o'clock now here in Austria. And we are ready to get going, right, Seda?
Yeah. Yes.
Indeed.
Again.
Okay.
Good morning.
All right. So good morning, Europe, and good morning beyond Europe. Welcome to our webinar and live session from the Spacesuit Laboratory of the Austrian Space Forum here in Innsbruck, Austria. My name is Gernot Grömer. I'm the director of the Austrian Space Forum, and I am an analog astronaut. So we'll talk a little bit the work I'm doing, the work we are doing here in the Austrian Space Forum, and share some pretty cool imagery in the beginning, and then we'll take a live tour to the Spacesuit Laboratory, which is right behind this wall behind me, and I'll show some of the hardware we are having here. So first of all, I will talk a little bit about planet Mars, just to give a little bit of a context of why we are going there and what makes the planet so interesting. And then we'll take a tour to the Spacesuit Lab, of course. And then at the end, there will be roughly 15 minutes or so of question and answer time, and giving you the opportunity to ask questions. By the way, because we have a slight technical delay between the live stream on Zoom and the live stream on YouTube, there is a 1 minute difference. We will also take questions anytime via the chat. So my colleagues, Gustavo Rojas and Seda Fritz, will be monitoring that, and they will pass on questions from all sides. So if you have questions throughout the webinar, feel free to write them down as soon as you like. And also at the end, there will be plenty of time to ask questions as part of the STEMMOS project funded by European Union Erasmus Plus program. So let's take a hike. Let's take a look. Let's take a voyage that takes us 380 million kilometers from our current location. And that is we're going straight to planet Mars. Well, first of all, it's a world that is roughly half the size of the Earth. And as it's 380 million kilometers away, it takes us humans to get there roughly 200 days per leg. So if you say going to Mars, and that's going to happen within the next 20 to 30 years, it will take 200 days to get there, roughly 1 year to stay on the surface, and then 200 days to come back again. So it's going to be a voyage of about 1,000 days, which is a long voyage, but we did this as humans before, previously in our history. Now, the world itself, it's smaller, has less mass, which means less gravity. That means you also have, you can jump higher on Mars, so to say. The world itself is a cold, dry, barren desert world, minus 70 degrees Celsius average temperature planet-wide. We have less than 1% of the atmospheric pressure of the Earth, which means we are anywhere between 7 to 11 millibar. That corresponds to roughly 35 kilometers altitude on the Earth. And even this little 1% is not breathable because it's mostly comprised out of CO2. 95% of the atmosphere on Mars is actually carbon dioxide. Minus 70 degrees. 1% of the Earth's pressure, high radiation environment. You have a soil that is chemically reactive, and some parts of it are even slightly toxic for humans, for instance. Why the hell would we like to go there? Well, first of all, there are people like Dr. Seda Fritz. She's a geologist. She's also with the Austrian Space Forum. She is tremendously interested in the geological paths of the planet. But that, when I come in from an astrobiology point of view, has a link to life as well. So let's take a brief look at the geology of Mars, saying, well, there's a few things that are resembling us of the moon, for instance, like impact craters, like impact basins, including the second largest impact basin of the solar system, the Hellas Basin, with 2,200 kilometers width. And there are mountains, huge mountains, including volcanoes, huge volcanoes to be more precise, including the largest volcano, the largest mountain in the solar system, which is Olympus Mons. You can see, I don't know if you see my mouse. Oh, sorry. First of all, you need to see the slide set obviously here. Sorry for that. Okay, just starting with the pictures here, so all good. And yeah, sharing, no, I think I'm sharing the wrong screen right now.
You're sharing, we see the Mars.
You see Mars in full screen, right?
Yes.
Okay, sorry about that. So what we see basically here is an overview of the entire planet. You see the polar caps that are covered with ice, mostly water ice. On the south cap, there's a little bit of CO2 layer there as well. You see impact craters, the basins I was talking about, and I mentioned this huge mountain like the Tarsus region here, that's the Himalayas of Mars. This is the place where you have this little, I think I can show here the mouse pointer here. You have this dot here, that's Olympus Mons. That's 600 kilometers in diameter, a mountain the size of France for comparison. And that is as high as 3 times Mount Everest, on a planet half the size of the Earth. So it's a planet of the superlative as well. If you like to go climbing, there is another fantastic location that I can recommend, and that is the Valles Marineris, the Marina Valley, which is the scar here, if you see my mouse pointer. So this thing here is almost 8,000 meters deep. It's a very deep abyss, and it's about 3,600 kilometers in width. So if on the left end here, on the western end, there would be Los Angeles, New York would be right on the other side. So this rift is, it's a graben, geologically speaking, is the size of the continental United States. And so, as I said, why the hell are we going there? What is the reason why we're putting so much effort and heart and blood and sweat into going to Mars? Well, it is its past. I said it's a dry, cold desert now, but it was not like this all the time. So we have very good reason to believe that about, oh, that was a bit too fast, that roughly 3.5 billion years ago, there was water on Mars. It had a much higher atmospheric pressure. It was warmer. It was a much more comfortable environment for life to be there. And so we know nowadays that Mars probably had 1 billion year liquid water on its surface, including lakes, rivers, even an ocean. And you see this here in the picture. This is a very old area where you see these layers, this strata, that's what we call sedimentary structures. Imagine this being a large, big lake previously, and all the aerosols settling down from the air, setting through the water to the ground, and building there layer after layer. And this is like a history book of Mars that tells us about its past. Well, it was warmer, had a thicker atmosphere, it had less radiation, had an intact magnetic field, had water on the surface. Well, these are all the ingredients you would need to start life, right? And so the big $1 million question is if life ever arose on Mars. And a lot of the research we're doing is revolving around exactly that very question. But we're doing this not alone, but we are setting precursors. We are setting scouts. And these scouts are non-human. They are, for instance, robots. Like here, the Perseverance rover, it is a 1-ton masterpiece of engineering that is able to analyze rock composition. It's not yet built fully for finding life on Mars, but first of all, we need to understand the geology, the context, so to say, so that once humans arrive there, we need to make sure they are looking at life signs at the right spots, the right places on Mars. And it also includes, for instance, flying robots. So right now there are 3 functional robots on Mars and 1 helicopter. That's the Ingenuity helicopter that has flown, solar powered, obviously, which was quite an engineering feat to make something fly on the Martian surface. Now, these are only precursors, I said. These are the trailblazers that lay out the path to the red planet. But one day, it's not a question of if, but only when people will follow. And I think right now is a good time to start with this. And that's what we're doing in the Austrian Space Forum. So we need spaceships, we need habitats or space stations, we need a science program, we need life support systems, and we need spacesuits, of course, to go outside the station. And this is what we built here. So you see here a sneak preview of two of my colleagues, one from Italy and one from the Netherlands, who are putting on the spacesuit right now. These suits weigh roughly 50 kilograms. They take about 3 hours to put them on and about 5 months of basic training until you're allowed to use them on your own. So it's, and you always need a team. It's a little bit like suiting up a medieval knight in his shining armor. And so we test them with the humans inside, obviously, but then we test them also in laboratory environments to make sure we know the behavior very well. For instance, can it survive a night on Mars? So we put the entire suit into a cryo chamber at minus 110 degrees Celsius and see if the thermal control system worked. And obviously it did, so the astronaut inside did not freeze to death. Or we know that there are dust storms on Mars as well. So the problem is, because the air is very, very, very dry, it builds up static electricity. Because if the sand particles are impacting each other and rocks on the surface, they can transfer charges. And that means they can be charged. So all the wind on Mars with all the particles is charged as well. And if you have a swirl wind, like a dust devil, for instance, you build up so much electricity that you can have lightning strikes on Mars. And of course, you cannot run from a lightning strike. So you have to build a spacesuit that is able to withstand a small lightning strike. And not only in the books or laboratory environment, but you really want to strike it with a lightning strike. That's what we do here. So put it to a Tesla coil. You might know this from physics teaching. Then in this case, a little bit bigger one with 6 megavolt, and make sure the suit behaves as predicted. And I was very happy that it worked out like our engineers had predicted, because I was the guy in the suit. So, and then once the suit survives all those laboratory testing, we make it dirty. That means we take it to Mars-like locations on Earth, for instance, to the Northern Sahara, to Israel, to Armenia, or in that case, what I'm going to show, to Oman, for instance, in the Dhofar Desert, one of my favorite deserts. I love deserts, I have to admit. And there are places that really have an astonishing similarity to the red planet. For instance, they just look like it. But not only that, they also have mineralogies that are similar to Mars. They have structures like sedimentary structures, old fluvial structures, like old riverbed structures that are pertinent to Mars as well. They have literally geological twins on the red planet. And so if you look at this picture, on the top, this was taken on the 15th of February, 2018. That's Oman, with 2 of our analog astronauts on spacewalk. We call this EVA, Extravehicular Activity, EVA, aka spacewalk. And the picture below was taken just a week afterwards on Mars. So these pictures are just one world, just a week apart, a little bit more, but they are 2 worlds apart, but still look similar. So that's an amazing part of doing analog research, that you are in this privileged position to understand that, yes, you're not on Mars yet, but you're mentally not fully on Earth either. That means you're somewhere in limbo and get a sneak preview of a world yet to be discovered. And you need more than the astronauts. You need many more people. We're talking about 200, 250 people from 20, 25 nations plus that are able to do those missions. You need to train them, have to make sure they understand the experiments very well. They know the technology, the safety has to be guaranteed, and so on. And then you go to the test sites, like here in Oman with this inflatable structure. That was my home for about a month. That was our base station, our habitat, as we call it. And when you try to go outside, you cannot do that simply by opening a door, but you have to go through an airlock, and you have to do this with a spacesuit. Otherwise, you would be on Mars very fast, very dead. And so every time you go outside, you have to do all the planning. Where are you going to go where are you going to go? What are you planning to do? And all of this is not only managed and coordinated by the crew in the field itself, but much more importantly, the Mission Support Center here on Earth. So I want to give you a quick introduction to this here. This is our ground segment that's in Vienna for analog research, a permanent mission coordination center, mission support center. that allows us to download the telemetry from the suits with time delay, because we have to account for the huge distances between Earth and Mars. So if Earth and Mars are 380 million kilometers away, that can take up to 20 minutes for a signal to travel one way. On average, it's roughly 10 minutes, right? And these are the people, flight engineers, medical doctors, psychologists, mission planners, Earth scientists, and so on, who are looking into the data in near real time and then tell us and the crew what to do the next day, so to say. So we're mimicking this quite well. But there's a challenge here that is really hard to overcome, and that is we can mimic the time delay, we can mimic the isolation, we can mimic the mechanical strain of the dust particles impacting on the spacesuit and so on. But one thing that is really hard to mimic is the lower gravity, because there is no isolation sheet you can put on the ground and then float above it. Obviously, would be quite cool otherwise, I guess. But so we're lacking that. So we had to think about ideas. How can we study the physiological, the medical, the body workload on the human body if we are on a lower gravity? Well, you can do this for a very short amount of time when you do what we call parabolic flights, when you have an airplane that goes up and down in a very specific pattern. At the top of this parabola, you can have up to 30 seconds of weightlessness or up to roughly 45 seconds of reduced gravity. So we can mimic lower gravity there. But that's only for a few seconds. There's not a lot of physiological studies you can do with this. But we have a solution to this. We'll call this the Vertical Treadmill facility. It's basically, I'll show you a picture here first, an instrument where you take a human in suspension with, you see all those wires that go up to the ceiling. So we are floating basically. And then you have a pulley system that drags you against a vertical treadmill, just like the one you use from when you go to a gymnasium or a fitness studio or so. But this one is tilted by 90 degrees. You're walking on the wall, so to say. And depending on the strain of this machine, you can mimic different gravity levels. And if you do this for the moon, you see a result like this here. So let me start the video. This is one of our analog astronauts, that's Dr. Robert Wild. He is a quantum physicist at the University of Innsbruck, and he is walking under lunar gravity. Be attentive, this is not a slow motion video. This is the real-time video here. And what you see, the movements are different. If you tilt your head by 90 degrees and watch the movie this way, this is what humans would walk like on the moon. And I'm going to show you exactly this facility in a moment in reality. So I would say we have our second camera prepared. Selina, if I may ask you, so going to quickly switch. And yeah, do we have a signal already? Are we good?
While we are waiting, I might mention about our STEMMOS project, Gernot, if I may.
Yes, please.
Yeah. So while they are switching the rooms, hello everyone. I'm Dr. Seda Özdemir from Austrian Space Forum, and we are now having this live stream from Spacesuitlab under the framework of STEMMOS project, and we would like to ask you to register our portal, please. I just shared the link in the chat. Because with this registration, our dear teachers or all education training activity people, you're going to get our newsletters from STEMMOS project, Earth, Moon, Mars observation related, and also lots of pre-review open educational resources. Please feel free. It is for free, of course, also. And we are waiting for your registrations and also your questions, please, in YouTube chat that we can relay to Gernot at the end of this session. Thank you very much.
Thank you. I'd love to hear from you. So if you have questions in the classroom, just put into the chat. I'd love to hear from you. So let's go into the lab now. So first of all, I would like to show you the Vertical Treadmill. This is what we call a ground-based facility of the European Space Agency, operated by the Austrian Space Forum. So this is a machine you just saw before. So you have the human here in suspension, you have the vertical treadmill. So we lay down here together with some machinery. For instance, we are measuring spiroergometry. So we're looking into the breathing patterns. We measure CO2 and respiratory patterns, look a little bit like I would say like a diving suit, like a diving breathing apparatus. We have motion capture cameras that tell us where exactly the body limbs are. And then we basically lay down like this. Below. Okay, this is just for safety. So once I'm in suspension, we can remove that, and then I'm floating. I can only indicate it here, and then so I go down here, and then I have here all the pulleys. And if I go down, I can. It's actually quite a nice fitness training you can do here as well with a quite expensive machine, I would say. So this gets pulled down, and then you are supported by this blue part here. And once I'm in suspension and floating in the air, so to say, which is quite a weird feeling, I have to say, then I can go on a treadmill. I have to hold myself here, and then I can start to walk like this. I'm now under Earth gravity, simulate, and when I'm on lunar gravity, I do it in a more gentle way like this. Of course, just imagine I'm floating here in suspension, so to say. So this is a quite exhaustive exercise, I have to say. I did it many times, and it's amazing on the feeling point of view, because when you're walking under Martian gravity or lunar gravity, and you just watched these magnificent panoramic pictures of Mars or the moon on a computer screen or on a book or so, and you close your eyes here, it's amazing that you have this full body immersion, that your body tells you that you are really walking on the moon. And that's an amazing feeling, I can tell you. If you have a chance to drop by, please, we can put people here on this machine for research and education purposes. Okay, so that's the vertical treadmill. It's quite unique. This facility is unique in the world. It's a prototype. There are others in the US, but from the precision point of view, the measurement opportunities, this is probably one of the best we have on this planet right now. But I think you wanted to see something else, and that is the spacesuits, right? Okay, let's have a look. We are standing here next to the AUDA spacesuit simulator. I just have to take my rings and my watch off here. I don't scratch anything. Actually, it's not only a spacesuit, it's almost like a spacecraft to wear. So this is a machine you can put on after 3 hours of putting on this suit, so to say, that mimics all the major limitations a real spacesuit would have on Mars. So it restricts your movement. You feel very isolated. It's heavy. It's putting quite some strain on your muscles. And it's quite a high-tech thing as well. So we're measuring right now roughly 50 parameters inside the spacesuit, anything from ECG to gas composition, power status, temperatures, whatever. Some of this can be read out directly from the suit itself. So if you can come closer with the camera, you see up here a head-up display. It's switched off, of course, right now. And the head-up display gives you all the most important data of the suit. So the astronaut knows always what their condition is and what the suit's condition is. This is all then processed in the backpack of the suit and then transmitted via high-frequency communication to an operation station, the habitat, basically, where we simulate the rest of the mission. Now, there's obviously lots of high-tech. Simple things are like a chest pack, which is on purpose almost empty, because that's a working surface. If you want to work with a rock sample, for instance, here's a command point for the telemetry display, for instance. You also have USB ports. You can put in like a small USB microscope that gives you a high resolution image of a rock sample you're looking into, for instance. There are some materials here that are really top of the line, like this titanium chrome vanadium steel. This has a very, very low thermal expansion coefficient. It's one of the hardest steels you can find in the industry. And that was necessary because we need to make sure that the opening mechanism does not change the form when it's getting colder anyway, because steel is very unforgiving on this. So lots of high tech. But because we have a human inside, of course, you want to make sure that this is taken care of as well. So yes, you can go to the toilet inside the suit. Yes, you can drink inside. You can eat inside, for instance. And also, we're taking care of another reflex, which is quite inconvenient. That is, when we as humans are exhausted, we start to sweat. When we start to sweat, we have the reflex that our nose starts to itch. Now, in this case, you cannot scratch your nose, obviously, right? And believe me, sneezing inside a spacesuit is a very bad idea for obvious reasons. All the mess will be on the inside and you cannot clean it, of course. So what do? Well, we have a very low-tech piece of solution here, and that is the blue part. That's called the RFD razzle-frazzle device, which is when every astronaut has its own, of course. This is my best friend, because if I start feeling that my nose is itching, I simply rub in my nose so I can avoid that I sneeze inside. Yeah? We have an exoskeleton that is mimicking the limitations of the pressurization, for instance, with external lightnings. We have the option that if, those suits always go outside in pairs, like divers. We always go in pairs. If one suit is low on power and the other still has more power, they can share the power. So on the side here, I think we can come to my side here. You see here ports where we can share with the umbilical power in between the spacesuits and make sure they are have similar power status so they can walk back together on Mars, right? So this is quite field proven, I have to say. By the way, I haven't mentioned that yet, but the name AUDA, that's the name of the spacesuit system, is not an acronym, but it is a homage to Jules Verne's novel Journey Around the World in 80 Days, Traveling Around the World in 80 Days. If you know that book, or there's also a Jackie Chan movie, I think, about it, there is an Indian princess he marries at the end of his voyages, and that's AUDA. And so to us, she is like a Indian princess. She's beautiful to look at, but she's also high maintenance. So she needs a lot of care, of course, like any princess does. And because she is a princess, we have another little tradition here. And that is when she goes on travel, so she's put into those travel boxes. And that because she's a princess, she always travels with a rose. So both suits, we have two suits, they always go with a rose, of course. So we have those traditions. All the data that are produced, not just local, submitted to the operation station, which we have right here. So these consoles, they are basically the logical representation of the habitat on Mars. So here we have two operators, also usually two crew members who are analog astronauts, who accompany the astronaut in the field, who tell them, well, pick the drug and move on to the next waypoint, for instance. So these ones are allowed to communicate in real time because they are on the same planet, right? Then the data being processed here, highly encrypted, and then they go to this black box here, that's a server box, and from here it goes to the satellite, and from the satellite to the mission support center. And so there, the flight controllers see the data with a 10-minute time delay. So that's also realistic. So whatever they see, they have to anticipate problems. They have to be very attentive of things that are yet to develop, right? You see here just the upper part of the suit, but I want to show you something a little bit unusual, and unusual, everything on here is a little bit unusual. That is, we are lucky from a timing point of view for this webinar, because we are right now building a museum version for the Steel Worlds exhibition in Linz at the Stahlwelten in Austria. And so right in the next room in the mechanical workshop, we have the almost finished, it's not fully finished yet, but almost finished museum version of the suit. So you see here the entire suit in full glory. Again, it's still in the making. It's not. It's just mock-up yet. It's not functional, of course. But if you come to Austria or to Linz, that's one thing you could take a look at. So there's a few things that are really, really high tech. For instance, also the material here, the textile that has been tested in a large European Space Agency funded project. We were testing for radiation absorption, for biological growth potential, for abrasive resistance, and so on. So this was a almost 3-year-long project that took us a while to understand what are the materials you could use on the moon, and this is a solution basically to it. So this is a material that actually you could use for a spacesuit on the moon or on Mars, in fact, really. So these are all simulations we're doing here, right? So this is doing as if, and we're still learning a tremendous amount of knowledge here. But how about flying things? How about really going into space? Well, we do this here as well. So the next step we're going to take as the last part of our journey through the Spacesuit laboratory is taking a look into the integration room for satellite hardware we have here in the Austrian Space Forum. So we are just moving to another room. You see it's a very small facility. And I'm going to walk into this room here. The camera cannot follow, unfortunately, because of cleanliness requirements. But I'll show you through this window what's on the other side, basically. So I'm going to put on, first of all, my lab coat. So these are quite fancy lab coats because it's a fun fact. If you look very closely, you see those little lines here, the pattern. This is not for fashion, but this is conductive wires. That means the entire coat is also avoiding electrostatic buildup. So that's good for working with electronics. And I gotta put up my overshoes so I don't get in some dirt from the road, in the street. And then my favorite part, this extremely fashionable en vogue top of the line headgear. And then I walk in. Oh yeah, by the way, what we're gonna see inside. We have been looking into the problem of space debris contamination. So what is that? There are more than 12,000 satellites that are floating around in low Earth orbit right now. So thousands of satellites, but not only satellites, but also upper stages from rockets, unburned rocket fuel, things like flakes from paint that come off, a loose screw, anything. Yeah. Most of those particles, and we talk about millions of those particles, are very small. That sounds very harmless. We're talking about, a fraction of a millimeter maybe. But because of the high energy, because of the high velocity, they have a high kinetic energy. And you think of it that if you remember physics, maybe, if we take, let's take here. Okay. The kinetic energy equals mv square half, right? If you increase the mass, you increase the energy. If you double the velocity, you quadruple the kinetic energy, right? And so a particle that goes up with, like, let's say, a few tens of thousands of kilometers, like 15 kilometers per second or so, hits you with a full brutal force. And these particles are rubbish. We don't want them, but they're still up there. So we humans have the talent that wherever we go, bring trash with us. And that is also including space, unfortunately. So space is less pristine, at least low Earth orbit space is less pristine as we think. And we wanted to measure how much of this dirt is up there. And so we built a satellite. This is a model of it. This is a 1:2 model, basically, of the Adler 1 satellite. That you see here the solar panels, you see here the body where the electronics and the power systems are. And you see this little concept, this plate here, it's just symbolic. This is basically like a microphone in space. It basically is a piezoelectric plate that once it's hit by a particle, it creates a small electrical signal like a piezoelectric piece does. And we analyze the signal and tell us a lot about the nature of the particle. Let's see how this looks like. So I'm going to change my position here. All right. So lots of electronics here, obviously. And we have an engineering model of, but it's a real thing, from the Adler 1 satellite. And I'm going to show it to you. So this is one of the panels. It's from the Adler 2 satellite, actually, but the idea is the same one, where you have here a very thin layer. It's like a printed circuit board, but just single with various layers. And in between, there are piezoelectric discs that are super precise when they hear. So you say, in space, you cannot hear anything because of the vacuum. Well, that is not entirely true, because a sound wave is nothing else but the mechanical shock wave. If it travels through air, but it can also travel through material. So if you have an impact here, the acoustic sound wave travels in the material, and that's what we record, so to say. And you also see there's this weird black and white pattern that was printed on top. It has no scientific function, but it was just a fun project. Actually, there's a secret code hidden. So this is kind of like a Morse code or so. So when all the wings are spread out, the satellite has a message to say, but it cannot tell you what it is. It still has not been broken yet, the code. So somebody will write an email, say, hey, Gernot, I've cracked your code, and I will be so happy. So that's part of the other satellite. Otherwise, this type of laboratory has lots of 3D printers, of course, involved as well. Some specific properties in terms of electrostatic discharge protected floors and ceilings and so on. So it has some special features in here. But otherwise, it's like working in an electronics workshop, just with some more careful gown here. With that said, I will slowly come out again. And we will be heading back to the office. And again, please remember that there is the opportunity for asking questions in the chat. And if there are urgent questions, we'll address them right away. And otherwise, we'll simply wait then until the end. Okay. So, I mean, this has clearly been done by people who who know what they're doing when it comes to electronics or to astrophysics or astronautics or so. So you might think that all of those things are for adults only and for the ones who have studied. Well, to some extent, yes, but to some extent, not only. So we think space is for everyone. And I want to show you an example of how this can work out. And I'm going to switch back to the other computer. Thanks, Selina, for being the camera woman. And I'll show you how we do this with younger people here as well. So what I'm going to show you now is, let's see if we have that one here running. Yeah, that looks good. Yeah. This is an example of a project where we deliberately involved young people as well. It is also a European Union funded project called EXPLORE, which stands for Expeditionary Program for Learning Opportunities in Analog Space Exploration. And the word expeditionary tells already a little bit what happened here. So we were inviting students from across Europe, from Greece, from Portugal, from France, from Austria, to join us in a project where they would learn about Mars exploration, but also experience it firsthand in an analog research environment. So we would take some of those students from 3 countries and fly them to Portugal and then drive them down to Monsaraz, which is a beautiful area that is also known for its magnificent night sky. There's a famous observatory there. And there we built the infrastructure that is the same like you, well, to some extent, same like you would have on planet Mars. And you would have people who will be living there, and we have the crew basically staffing the mission control center or mission support center with flight director, with remote science support, with the flight planning and so on. And then the crew itself, you see here some of those from different countries that were actually trained to use the spacesuit simulators. They're slightly more simpler than, of course, the OeWF spacesuits, but basically the isolation feeling is quite similar in those suits. And they will also go out and choose rock samples to experiment from astrobiology. They will also do human factor studies. So it's really a number of research activities they would do that are similar to what you would expect on Mars as well. And we have already started, or we are just starting now our follow-up project. So EXPLORE has already a second mission in the pipeline in April next year. And there will be also a project that is following up on the EXPLORE project in general. That's called SPHERE, like the ball, SPHERE. And we are also still looking for students or for school classes that might be interested in going on analog missions in Portugal as well. And we have a couple of really, really cool things in the pipeline that you might want to take a closer look. But for now, we are focusing on the STEMMOS project, satellite observations of Earth, Moon, and Mars in schools. So as I said already, please, if you want to do me a favor, go to the website in the chat and sign up there, not just for this newsletter, but there's a tremendous amount of didactically really thought through material that can be used in school classes for free. And we put a lot of effort in creating material that is easy to use, easy to be injected in several subjects in school, And I know from experience that students have a tremendous amount of fun and inspiration by using actual satellite data like we do for the STEMMOS project. So having said that, that slowly brings me to the conclusion of my of the showing the suit lab. There's more to see, of course, but I don't want to spill all the beans in the first place. Also, if the topic of analog research is of interest to you, I wanted to share some quite exciting news, and that is starting next week on the Monday, the 13th of October, we will have again a Mars analog simulation, but not just with one crew on Mars, but we're talking about what if we think about the time when there will be not one station on Mars, but let's say half a dozen of stations on Mars, half a dozen of stations on the moon, one spacecraft in transit. And that's exactly what we're doing for what we call the world's biggest analog. So it's really exactly as it says, it's the largest undertaking of a Mars analog mission ever done so far. And all of those 17 habitats on 5 continents will be managed and coordinated from Vienna, from the Mission Coordination Center of the Austrian Space Forum. So Seda and I will be busy as hell. It's going to be a very, very exciting time. 2 weeks is the duration of the mission itself. We've been preparing for this for 3 years now. And right after this webinar, I'm going to jump into my car, drive 5 hours to Vienna, and do the other final preparations for the mission and the startup of the Sphere project. So it's going to be quite a rough ride, I guess, but it's fun. It is really rewarding because you get to work with so many talented people from across Europe, across the entire world. This is really the magic of this profession, that you are getting a sneak preview of things that are yet to come, that you see futures that bring together people that are working at the edge of what's technically possible. And above all, the topping of the ice cream here is that you get to explore new things. So there are days in my daily life, and the same for Seda's life and for Gustavo, that when we walk out from the office, from our laboratory, we know we have found something new that nobody else had known at the beginning of the day. And that's one of the magical fairy dust items of science. I can really recommend it. It's a very, very unique feeling, I can say. And so that basically brings me towards the end of this session, and I'd be happy to hear your questions. I don't know if there are already any questions on the chat.
Thank you very much, Gernot. Wow. Actually, we have some highs from Greece and Portugal.
Oh, really? Hey, hello.
Yes. And then Teresa Souza, you know already from Explore Project, one of our explorers teacher. And she is telling us the panel, the Adler panel code seems a genetic code.
Indeed, yes.
Is it a genetic code?
Sorry, I didn't get that.
The Adler panel.
Oh, so yes.
The code on the Adler panel seems like a genetic code.
No, it's a language code. It's a language code. Yes, it's all online. So if people want to dive into this, if you are a code cracker by nature, that's a tough cookie to crack, but it's worthwhile. I know the answer, but I'm not allowed to tell. So.
Damn.
Right.
Okay, so again, Teresa was asking if we can link this project to J Academy. I think I can answer that one. I already wrote. STEMMOS and the J Academy has also similar resources, but as I said, the combining the resources or linking them would only elevate the research and the task that you're doing. So feel free to do that, Teresa, with your students. And another one is again from Teresa, and the students ask me if they can also register in STEMMOS portal. As far as I know, we have only the teacher's registration link. Gustavo, if you're there, can...
Yes, I'm here.
Yeah, so can students also register to the platform?
The portal, the registration is intended for teachers because they will do the training courses on the portal, but most of the content is open without registration. So the students can access, the resources, the tools, without registration. So if they want, they can register. Of course, the registration is open to everyone, but it is intended for teachers, the content that requires registration. But most of the resources and tools, they are available even without registering.
Wonderful. Okay, please feel free to drop your questions in the YouTube chat. We have still some time. And also we have a minute delay, so we wait a little bit more.
Yeah, if I may add, we have a very good attendance today. We have about 35 schools watching us live. So that means, over 500
There
students.
must be some questions. Guys, 35 schools, this is your opportunity to ask direct questions about how weightlessness feels or so, anything.
Not we have questions. Wonderful. You wish it had become true. Okay, from Maria Kotsakosta, Alexandria from Greece. We would like more information about the helmet of astronaut and the gloves.
Okay, well, all right. So for the helmet itself, the helmet is a high-tech tool as well. So when you put on the helmet, automatically the display goes on. It also shades from the sunlight, which can be quite bright on the moon for sure, on Mars also a little bit as well. It has also ventilation inside. The helmet is also the mounting point where we have the water feeds, so we can actually, like a platypus, from bicycle riders, we have a similar system where you basically bite in and you can drink. And at the neck ring, there's also a part where you can put up a granola bar. Yeah, it's not much, but if you're out there for a couple of hours, a little bit of proteins is quite, and the calories is quite nice to have. So basically stabilize the helmet from the outside, and then we go like a squirrel and nudge it off. Yeah, we just need to be careful that there's not a lot of breadcrumbs, because all these crumbs go into the suit and then it starts to itch, and that's not very cool as well. So that's for the helmet. Also the visor is a special material, so it's a coated PMMA, polymethyl acrylate, which is also blocking part of certain part of the spectrum to not get a sunburn. But still, you have a Snoopy cap below that also helps you to contain the sweat. And then the communications carrier with the radio. There's always a backup radio there as well. So independently, there's a second mic and second loudspeaker inside that's in ear. So sometimes I'm listening to two voices at the same time, which is quite a focus thing for sure. Yeah, and for the gloves, that's the tricky part. Glove design for spacesuits is one of the most challenging engineering feats, because you really want to maximize your ergonomics. And our hand, and that's what you learn when you study glove designs, our hands are nothing less than a miracle of bioengineering. The way how we can move our fingers, how we develop force, how we feel things, is amazing. So we have several layers. We have first a comfort layer, that is a cotton layer where we can sweat into. Then we have the mechanical middle layer that is for the counter pressure simulation. It also has, for some versions, we use a little programmable interrupt controller, which is a little computer basically that measures temperatures and so on, and then guides it onwards to the main part of the suit. And then we have the outer layer. Yeah, that's the one you see when you look at the museum version, for instance, right? So you have the silver material on the outside, and then a very special grip material on the other side that is also conductive. So you can touch a touch screen with the spacesuit, and it still works. And it also has a certain pattern on the surface. And this pattern, especially the fingertips, for some of those, we have versions with this very bright orange little nipples there. This is for increasing our touch. And those little parts and the fingertips, they are mimicking one of the most fascinating sensoric inputs we have as humans, and that's the feeling of our fingertips. Now, if you look at your finger, you see the fingerprints, right? Have you ever asked yourself why we have fingerprints, except for the police, maybe? Yeah. Well, the thing is, these are increasing our sensitivity because our fingerprints, if you look at them with a microscope, you see a few things that are higher and a few things that are deeper on the rills of the fingerprints. And so when you go across the surface, those little bumps here, they are bended just a little bit on a microscopic scale. And our brain is able to interpret this. So the resolution of how fine we can feel with our fingertips is much higher than you would guess just from the number of nerves that are up here. And so we try to mimic this in the spacesuit. That means these little nipples we have, these orange parts, they are mimicking the fingerprints, so we can increase a little bit the tactile sensitivity of when we grab stuff. It's like, think of putting on a jogging glove, a sports glove, and then putting on a skiing glove, and then try to type up something on your keyboard or bind your shoelaces, yeah, with a 50-kilogram object on your back. So it is hard work. You got to train for that for sure. Yeah? So the spacesuit gloves are really, they look simple like a normal glove, but they have quite some ergonomics behind them. Thanks for the question.
Oh, we are having more questions. Wonderful. Okay, Gabriel from Nice, Greece. Students from Nice, I hope I spell right, want to know the way of the suit and the temperature on Mars. And
Okay.
they also want to know where they pee.
Okay, the question, of course.
Yeah.
So the weight of the suit itself is about 45 to 50 kilograms, depending on the configuration. So it's more than half of my body mass I'm carrying, right? Then that's the weight of the suit itself. Now, when we go to Mars, the temperature there is minus 70, as a 70 degrees Celsius on an average. So it can be as low as minus 120, minus 130 degrees. It can go up just above the freezing point of water. So we can go up to like 10, 15, maybe 20 degrees. If it's really a heat wave on the equator, it's the same thing like we would measure 6 degrees Celsius in the Death Valley on the Earth. Yeah? So it's really extreme high. So usually you are barely reaching the freezing point, so to say. Yeah? Did I forget a part of the question, or was the third one, I think? The weight of the suit, the temperature on Mars.
And the pee situation.
And the pee, of course. How could I forget that one? Okay, so for men, it's pretty straightforward. So we have a mixture between a urethral catheter, like they have in hospitals. You have a bag where you collect the urine, and you have a pipeline, and then it's like a condom basically, and then you can do number one very easily. For our female analog astronauts, it's slightly different. We have it looks like a diaper. It is an adult diaper, but we just call it differently. We have a few modifications here. It's called the MAG, Maximum Absorption Garment, and it's like an adult diaper, and that it has a very, very effective absorbent material inside that also absorbs all the odor, all the smells. So it sounds weird, yeah, but in fact, you get used to it quite fast, and then it works quite well. Yeah? So you don't have to abort your extravehicular activity when you're outside in the spacesuit and you think you need to go to the toilet. Would be very inefficient otherwise.
Well, a bit more questions is coming. Yeah. Teresa from Portugal again. Could the spatial suit fact not have a system with thin tubes containing coolant? Spatial suit. Okay. Could the spatial suit not have a system within thin tubes containing coolant? I guess she's asking about the cooling system of the suit.
Yes, sure, yes. Okay. Well, actually, spacesuits that are used at the International Space Station have exactly that. They have an underwear that is called the Liquid Cooling and Ventilation Garment, LCVG. And that's like a pajama with tubes inside that have liquids circulating. Now, the problem is, it's easy that the liquid picks up the heat of the body. The problem is, how do you get rid of the heat in the pipelines? And so they are using something that is called evaporation cooling. That means you push the liquid from the tube over a surface that has a lot of porous material, and parts of the liquid are evaporating into outer space in the vacuum of the low Earth orbit, and that cools it down very efficiently because you have a phase transition. I'm simplifying here a little bit. It's actually a double phase transition, but anyway, this works quite well, and we would use this for the Apollo missions on the moon, and we would use it for the open space, the International Space Station, and so on and so forth. The problem is, this works only in high vacuum. Once you go to Mars, that little crappy atmosphere that is there has just too much of a pressure so that evaporation cooling would be working. So you have to do different things. And to be honest, that's still a challenge. There are a few solutions out there that work with heat radiators, with heat pipes, for instance, heat sinks that are inside the suit, for instance. There have even been attempts of, just put a bucket of ice cubes inside the suit, but that only works for a few hours, and then they're melted as well and just carry water weight with you, so it doesn't make sense as well. So it is indeed a challenge that is not fully solved yet. So we always have this perception that spacesuits are a technology that is established and safe, and we know how to do it, just like a diving suit or so. But for Mars, it isn't. There are still a number of engineering challenges ahead of us. Do we have one more last question?
Yeah, we have actually plenty of questions still.
Oh, I think we have to restrict it to like one more question.
Lots of greetings from Pakistan as well. Hello, Pakistan.
Oh, greetings. Wow, that's a long distance. Great to have you on board. Welcome.
Okay, Martina Tansi, we are the students from Keshasmeni School. I hope I'm spelling right. So they would like to ask more information about the data we can receive from helmet, and what we can do if there's a leak in the suit. How you deal with it? First the data, second is the leak. Yeah.
So for the data, as I said, we're measuring roughly 50 parameters. That's more parameter than the astronaut needs to monitor, because some of this is done automatically or by the mission control center back on Earth. Now, what we need to see on our head-up display immediately are things like atmospheric composition of our breathing air, my heart rate, how much power do I have, how much is my connectivity. And then we can have other things like we can transfer a video from another suit, or we can put up a map that tells us where to go, like a navigation device in your car that tells us where your navigation point is, the next one, where's your partner, for instance. So that's all displayed in the suit, and I have this little chest pack, like a game controller, where I can swap from one screen to the other. That's a lot of data, especially the video data, which need to be compressed inside the suit to keep the data volume low. And all of this is then transmitted to the operation station, and the majority of this data that gets transferred then to Earth. So there's an entire chain where at the end of the day, all those data I produce in the suit are archived in a scientific data archive. So even years after a mission, a researcher can take a look at those data and analyze how did the heart rate correlate with the CO2, for instance? How did, under those particular circumstances on that particular day 3 years ago, how did the astronaut behave, for instance, right? So that's for the data part. Now for the leakage part, remember we have a simulator, so it's not fully qualified for Mars exploration yet. Now, if you would have a leakage in an actual spacesuit, that's very bad, of course. It's not like in the movies that your head inflates and it bursts up or so. That's not the way it happens. So when you have a leak, the most likely leak to happen is from a scratch from a sharp surface or from a micrometeorite. That is a very tiny hole. You have an emergency backup pressure vessel inside your suit that you can activate, and it gives you, depending on the size of the hole, even like a half hour or so to go back. So if this happens in the vicinity of the space station, you can usually make it back quite easy. It was never used before, so it was never needed, but we have it. For Mars, there are no micrometeorites on the surface because the atmosphere is just thick enough to absorb the little particles quite well. So you would have a shooting star, basically, unless it's really a big one. There is an idea out there that if a bigger one comes in, you can still mitigate that. And that is that you have two layers of like neoprene layer, like in the diving suit, for instance. And in between this layer, you have a foam, like a liquid, a very thin liquid layer, basically. And once the outer hull is compromised, that liquid changes the phase. It's like getting rigid because it has contact with CO2, for instance. So it's self-sealing. A comparable system would be when you have car tires, and if you have a flat tire, there are systems where you can pump in a foam to inflate the tire again, that you can make it into the next service station, so to say, right? So that is an opportunity. The suits themselves are built quite sturdy, so they include also a bulletproof vest, so little particles can impact and don't do a damage. All right. I'm sure there must be many core questions.
Two things I would like to add. Uzbekistan and India is also here. We would like to say hi to them again in far distance.
Hi there. India has a tremendous space program. It's the fourth largest space agency in the world. And I think that's something that is totally underestimated in the Western world. You guys are doing great stuff in India, and good luck for your first human space flights.
Yeah, thank you very much. There are lots of thanks in the chat as well. Gernot from Athens, from Greece, from Portugal, and all other countries that they are with us right now. And yeah, thank you very much to you
Thank you very much.
Opportunity that you shared from Suitlab.
Absolutely. Stay curious. On to Mars.
On to Mars.
Thank you.